We're going to continue working with particle equilibrium, but now we're going to move from 2 dimensions to 3-dimensional problems. You see, we spent a great amount of time dealing with the 2-dimensional cases that we've done previous to now. We've done lots and lots and lots of problems, because the truth is, once you understand the concept of what you're doing with equilibrium, and working in 2 dimensions can build that experience in practice. Once you get that experience in practice, moving to 3 dimensions is just like a little additional step forward, extending upon what we've learned in the past. So make sure you're comfortable with all of the 2D problems that we've done. Now we're just simply adding a 3rd dimension. Now when we do equilibrium in 3 dimensions, the problems are necessarily going to get more complicated, because we're basically increasing the amount of equations we have and the amount of things to keep track of. But fundamentally, the condition for equilibrium is exactly the same as it is for 2-dimensional cases. In other words, we look at the sum of the vector forces acting on the particle, or the center of mass of the object, and the sum of those forces have to be 0 in order for equilibrium to be reached. So and I'll just say equilibrium. And this is exactly what we wrote before. The force acts this way, force acts this way, force acts this way. The weight might act down. We sum all of those forces together vectorially. That's why there's a vector bar on top of the F. And if the sum of those forces, including the weight, sums to 0, then that means the object is motionless, or it's moving at a constant speed. It's not accelerating. But anyhow, it's typically we talk about acceleration, so it's not moving. Now, if you remember back to the 2-dimensional case, we said that the vector form was given by this, but we said that we sometimes can use the scalar form of these conditions. And if you remember back from before, we said, I'll switch colors here, we said that the scalar form of this vector equation in 2 dimensions really just boils down to summing the forces in the x direction equal to 0, and we had to sum the forces in the y direction equal to 0. And now that there's a 3rd dimension, you might guess that since there's 3 dimensions, we're going to sum the forces in the z direction, and they have to also be 0. So the extension from 2 dimensions to 3 dimensions is exactly what you might expect. Notice there's no vector bars over here, because now we're dealing with scalar quantities. So you still have to keep track of signs, and we still use the same sign convention, positive x that way, positive y up, and so on. Or I guess typically it's in a 3-dimensional system. We typically draw a 3-dimensional system more like this. So x, y, and z. So positive x is this way, positive y is this way, positive z is up. And if we go, for instance, this direction along x backwards, we have a negative component of a force as we're tracking things. So as we draw our free body diagrams, we're going to typically be drawing them in 3 dimensions. And so as you write things down, if you end up using the scalar form of these equations, you need to keep track of if your force is positive or negative, depending on your sign convention. It's the same as we've done in 2 dimensions, we're just extending it a little bit. Now this is the scalar form, but the full form of the vector form of this condition you'll see in books. I mean, this really is the vector equation also, but if you want to break this up and maybe have a little more detail, it goes something like this. The sum of the forces in the x direction, we'll put an I hat vector, plus the sum of the forces in the y direction, we'll put a j hat vector, plus the sum of the forces in the z direction, k hat vector, is equal to 0. You see, everything on the board here is saying exactly the same thing, they're just writing it a little bit differently. And I'm mostly writing this all down for you so that when you read your book, you're not really confused what they're trying to tell you. The master condition is that the sum of all the vectors acting on the point is 0. But if you blow that out into its real vector form, all of the vectors that you're summing together, they're all going to have an x component. So if we sum all of the x components, is what we're doing here, of all of the vectors we have, that's going to be the x component of the vector sum. And if we sum all the y components of the vectors we have, that's going to be the vector component of the y component of the vector sum. That's why I have a j hat there. And the same thing for k. So if the sum of the x components in the I direction is 0, and if the sum of the y components in the j direction is 0, and the sum of the z components in the k direction is 0, all of these things sum up to be 0 individually, then basically it's exactly what we've written down here in scalar form. So this is what you would see as a vector form, but this is really the conditions that you end up following in practice. The x components have to be 0, so this ends up being 0. The y components end up being 0. The z components equal 0. It's just writing it down as a full-blown vector. So Practically speaking, we end up just looking at, if the problem is simple enough, breaking everything into x, y, and z components and summing them together. Sometimes we'll keep the vectors in Cartesian form and just add them all up and so on. I think that this can be greatly explained in a quicker way by tackling a problem. But in the back of your mind as we do this problem, just keep in mind that we're not doing anything different than we've done before. We're just looking at the forces, writing them down as vectors, and we're adding them up, and they have to sum to 0. So that's what we're going to do here. Here we have a problem where we have a box that has a 40 Newton weight there, and these red lines, these are ropes. So really, you have to think in 3 dimensions, okay? So there's an XY plane here, and there's a rope suspended from the origin that has this box. There's a rope attached to a support that's attached to the rope here, and there's another rope here, and there's another rope here. And these ropes are all supporting the weight of the box that's hanging down below, okay? So you have to use your 3-dimensional brain here. I tried to, in green, kind of draw the ZX plane here like this. So you can kind of see that one of these ropes kind of comes over this way, and one of these ropes goes behind this plane over there like that. So you can kind of see the way I've drawn it here. If this is a slice of the XZ plane here, this rope is actually behind the plane a little bit, and this rope is in front of that plane over here. So I try to draw it a little bit for you, but I know it's a little hard to see there. The first thing we do when we solve any problem is we write a free body diagram. So let's go ahead and write a free body diagram. The center of the universe of this picture is right over here. So we're going to draw a dot there, okay? And that's labeled point A. And the other thing we're going to do is we'll always try to draw our coordinate system. So here's Z, and here we have X and Y and Z, okay? Now on top of this, we know that there's a rope going this way, and we know that there's a weight going down. So first let's draw the weight. That's a vector. So the weight is 40 newtons. Now there's a rope attached here coming along this axis purely, okay? And we're going to call that, we're asked to find what are the forces in all of these ropes. That's what we're really trying to calculate. So I'm going to call this F. Notice it goes from A to D, so I'm going to call it FAD. I could call it F1, F2, F3, that's fine too, but I'm going to call it FAD. And then I have 2 other forces, and they're a little difficult to draw here, so I'm just going to draw them like this. And this one is AC, so this is going to be called FAC, and this one's called FAB. Okay, and they're all basically attached to the same point in the center, which is the origin, which is where my box is attached. So 3-dimensionally, this is what I basically have here. And fundamentally, all I really need to do is figure out a representation for this vector in 3 dimensions, find out a representation for this vector in 3 dimensions, this vector in 3 dimensions. I already know what this vector is. It's 40 newtons pointed down in the negative z direction. If I sum all of those things together, then the condition for equilibrium means that they all have to be 0. Whenever you add them all together, which means the sum of the x components has to be 0, the sum of the y components has to be 0, the sum of the z components has to be 0. When you do all of that, the thing's in equilibrium. So the only trick to this problem is figuring out what these little vectors are. So hopefully you're given enough information from the drawing to figure that out. Now, all of these vectors, if you look at our free body diagram, they all start at the origin and they point outward. And we suspect that that's the case because this box is pulling down and these ropes are attached. These are attachment points, like they're attached to the walls or something like that. And so when you pull down, we suspect the ropes are pulling up like this. We don't know for sure, clearly, but we make an assumption in our drawings. So all of these vectors start at the origin and they end at their destination termination point. So if we're going to start writing vectors, let's start with FAB. It starts at the origin and it ends up at point B. So let's write that vector down in terms of what it would actually look like. So the FAB vector is going to be equal to the magnitude of FAB, which I don't know. They're asking me what is the force in all of the ropes. That's the force AB, the tension in the rope. That's what I don't know, but I'm going to leave it like this. And the vector form of this guy is going to be the force in the rope times its unit vector in that direction. To start things off, what's going to make things a whole lot easier is let's just write all of our points down here, all right, that we have here. Point B, what is that? The x component, notice that this is positive x, this is negative x, so since it goes here and this is the x component of this guy. It's going to be -3 for x. The y component of this guy is what is it doing in this direction. You can see that this is y is equal to 0, but it's going that direction, since I've got it drawn like that, and it's gone -4 in that direction. And the z component is how far up it goes, which is this, which is labeled here, which is +8. Okay, that's going to be helpful. The c, the point c is very similar, a little easier to read actually. The x component again goes back -3. The y component now is positive this direction along y, so +4, and the z component is the same, 8. Now what is d over here? D is the x component is, what is this number right here? You get to the x component here of what point D is, and I didn't actually give you a length here, so you can't really write, we don't really know what this point is here, so you think you're kind of stuck. But for now, just erase it. You'll find out later that you really don't even need to know this distance, and that's why we didn't give it in the problem. But in order to find this vector and this vector, I need to know the starting point, which is all zeros, the origin, and I have the ending point of everything. Now that I have those written down, I can more easily write a unit vector in the AB direction. A unit vector in the AB direction. What is that going to be? Well, if I'm starting at the origin and I'm going to point B, it's going to be -3 in the I direction, -4 in the J direction, +8 in the K direction. Okay? That is the direction, that's the position vector, but in order to make it a unit vector, I have to divide by the magnitude of everything squared. So -3 squared plus -4 squared plus 8 squared. Just like this, okay? So ultimately what this is going to be equal to is whatever FAB is, the tension in the line, right? And then inside of here, this is going to be -3I minus 4J plus 8K. And on the bottom, when you take all these and square them and take the square root, you get 9.43, okay? So all of this is just to basically formulate an FAB vector. Okay, so when you do all of this math, when you take the -3 divided by 9, when you take the -4 divided by the 9.43, the 8 divided by the 9.43, and then you distribute the FAB in, what you're going to get for FAB vector is -0.318 FAB in the I direction minus 0.424 FAB in the J direction, plus 0.848 FAB in the K direction. Make sure you understand that. All we're doing is we're doing the division of everything here. That's where the numbers come from. The FAB is distributed into every component that remains. That's why the FAB is everywhere. And the IJK is, of course, they can't ever disappear. Those are just the vector components written down. So basically, we have to do this process for every rope on the drawing. We need to figure out what that vector is so that we can add the components together. So that's important. Now let's move on to the next vector that we have. That was AB. That was this force vector pointed up. What is this one here? It's going to be very similar. It goes from point A to point C right here. Since we're starting from the origin, it's real easy. This is the X component, the Y component, the Z component there. So if we wanted to do FAC as a vector, it's going to be whatever the tension is in the line times a unit vector in that direction. And again, the X component is -3 in the I direction. This time +4 in the J direction, +8 in the K direction, okay? And then on the bottom, it's the square root of these components. So you have -3 squared plus 4 squared plus 8 squared. So ultimately you have FAC -3I plus 4J plus 8K. And on the bottom, this numbers, when you square them all, it actually also equals 9.43. The reason it equals 9.43 is because these numbers here, the only difference is that one of these components had a negative in there, and that's because of the symmetry of the problem. One of these ropes goes behind the plane, one of these ropes goes in front of the plane. The lengths of the ropes are really the same. They're just kind of equidistant on either side. They're spread apart. So really, these vectors are going to look very similar. So we do the same kind of thing. You divide each of these components, multiply FAC in, and what you will get for FAC as a vector is -0.318 FAC in the I direction plus 0.424 FAC in the J direction plus 0.848 for 8FAC in the K direction. And again, that's very important because that's our second force vector. I told you over and over again when you would do your mechanics problems that you would end up doing the same sort of thing over and over again. You would end up finding your force vectors, force along a line. This is force along a line that we've done before. You have to do it for almost every problem. You'll get kind of the hang of it after a while. Notice again, these vectors are very similar. This is the same. The only difference here is the negative sign. That's because of the symmetry of the problem and the way that the ropes are laid out. Now I need to find my third force here, like this. Now typically what you would do is you would say, well, it's the force in the line times whatever unit vector there is in that direction. And you would use the end point and the starting point to be able to figure that out. But in this case, I didn't give you this distance here, so you kind of get a little stumped. And then you realize, wait a minute, this rope, it lies purely along X. It lies purely along X. So the unit vector in this direction is just the X direction, or the I hat vector. So you don't even really need to do a calculation. The force that lies along AD, right, is just simply, and it's in the positive direction, it's just simply whatever the tension AD is lying purely in the I direction. See, all of these other guys, they have mixtures of I, J, and K because those ropes are oblique. They each have a little mixture of X, Y, and Z because the ropes are pointing obliquely. This rope points purely along I. So the tension, the vector form of it is just going to be whatever you'd have the tension there and purely in the I direction. So you don't even need to really know its endpoints to calculate that unit vector. You know what it is just from the drawing, and that's why I told you that we would get to that point and discuss that later. Now the last force in our free body diagram, because we need to sum all of the forces, is the weight. And the weight acts purely down, which is in the negative Z direction, which would be the negative K direction. Again, I don't have to have any endpoints because I know it's pointing purely in one of my primary directions. So the way I write this is the weight of this object is negative 40 in the K direction. It's very important to make sure your sign convention is there. It has to be negative 40 because it's not pointing up, it's pointing down. And you have to keep track of that yourself, all right, by doing it there. This guy was positive because it was pointing along positive I direction. So ultimately, what we're going to end up doing for all of these guys is we're going to end up following the condition of equilibrium. So for equilibrium, all of these four forces have to sum to be zero. So what that means is FAB, which is the force in the AB rope, the vector force of it, plus FAC, the force in that rope, plus FAD, the force in that rope, plus the weight, has got to be equal to zero if this thing is going to be in equilibrium. All right, and so that's what we're going to do. So what this is basically saying is, if you look at FAB, we calculated that before. I'm just going to write the whole thing down again, which is going to be negative 0.318 FAB in the I direction minus 0.424 FAB in the J direction plus 0.848 FAB in the K direction. And just to prevent your eyes from bleeding and all the red here, that's FAB. We're going to add FAC to that. So we're going to add this whole thing on the next line minus 0.318 FAC in the I direction plus 0.424 FAC in the J direction plus 0.848 FAC in the K direction. That's our next vector. Next, we need to add FAD, the other force. That's a very simple one. So here we'll have plus FAD in the I direction. And then we have to add the weight in, so it's minus 40 in the K direction. This is equal to 0. So when we have something that we say sum of the forces has got to be equal to 0, sum of the vector forces, what we're really saying is we have to literally find a vector representation of every single force, add them together, and set the result equal to 0. If we can solve that vector equation, we've solved everything. We know the forces inside of everything. But notice how compact this looks. It looks very simple, but in reality, really it's a giant mess because you have one vector, which is 3 dimensions, another vector, which is 3 dimensions. This vector, even though it's only an I, it's still x, y, z. It's just the other components are 0, and also this is 3 dimensions. So basically, for every vector you have, it's a 3-dimensional deal. So what we need to do is figure out a way to solve this, and this is kind of where the scalar parts come in. See, the only way this equation can happen, the way you add these things together, see, first of all, you want to avoid the trap. So you might look at this, you might say, oh, negative 0.424, positive 0.424, I'm going to cancel these. But you can't do that because this is 0.424 times a force, FAB. This is 0.424 times a force, FAC. You can't just add these together. All right, because they're different. They're multiplied by different forces here. You also can't just add these together and just say 0.848 plus 0.848 because you've got different forces here. So it's like X and Y. These are totally different deals. But what you do need to do when you have a vector equation like this is you need to add everything component by component. In other words, for this vector equation to actually be equal to 0, what it means is that the sum of the I components need to be equal to 0. That's one equation. The sum of the J components of everything need to be equal to 0, and the sum of the K components summed together need to be equal to 0. This is exactly the same as we've been doing before. We've been summing the X components and summing the Y components together all the time in our two-dimensional problems. The reason that happens is because in the vector form we need to make sure all the components separately sum to 0. We're just keeping track of it in 3 dimensions with the vector form. So if we're going to set each component, and when I say component, I mean the ijk component equal to 0, then what we're going to have here is for the I component, what are we going to have? We have 0.318 times FAB, right? And then we're going to sum it with the other I component, negative 0.318 FAC, and then this is an I component. So we basically add all the I components together. So what we have is negative 0.318 FAB minus 0.318 FAC plus FAD is equal to 0. So this is basically summing making sure that the I components or the X components of everything sums to 0. Now we're going to look at the J components. It'll be this plus this, and there is no J component anywhere else. So for the J component, what we're going to have is negative 0.424 FAB plus 0.424 FAC. And I'm going to skip a spot over here, and I'm going to say equals 0 over here. You'll see why I'm kind of skipping that spot in a second. The K component, we're going to sum all of the K components and make sure they're 0. This component plus this component plus this component has to be equal to 0. So when you do that, what you will get is 0.848 FAB, and then we have plus 0.848 FAC. So we're doing this component plus this component. This component is going to be also added in, but it's a constant. Notice there's no FAB, it's just a number. Typically we want to move the numbers to the right-hand side of the equal sign, so we'll make it positive 40 by moving it over. Really it's minus 40 equals 0. We're going to just move it over now. The reason I'm doing it this way, when we set component by components equal to 0, you end up with a matrix set of equations. You end up with 3 equations and 3 unknowns when you really look at it. We have FAB, FAC, and FAD. These are our 3 variables, and they're just numbers on the right-hand side. Now notice the way I've done it. I've lined everything up so our variables are FAB, FAC, FAD. This is FAB, FAC. There isn't FAD here, it's just 0, and then AB, AC, and this will be 0 here. The reason I lined it up like that for you is because ultimately you're going to solve the system of equations. I'm not going to do it for you because there's several ways to solve equations, and I already told you we're not going to solve every system together. It just takes too much time when really all you're going to do is type these numbers into your calculator. This will be your coefficient matrix, number, 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 number. Just don't forget to put the 0 in here. Number, number, number. Don't forget to put the 0 for FAD here. So you have a square matrix on the right-hand side. This is your column matrix. You hit the solve button on your calculator, and what you're going to get is FAB 23.6 newtons, FAC 23.6 newtons, FAD 15 newtons. This is the solution to the problem. Now, whether or not you type these numbers into a calculator solver and you hit the button to solve the equations, You can do it that way. You could also make this into a matrix. This is matrix A, and this is matrix B. You could take the inverse of matrix A and multiply times matrix B if you've done matrix math before. You could also solve this by substitution, addition. I mean, there's a million different ways to solve the system of equations. So there's no right way. But typically in engineering, you're allowed to use whatever ways you can and want. So you put this into a solver, which does the heavy lifting for you, and then outspits your numbers. The most important thing in these problems is making sure you understand what you're doing and making sure you understand the concepts. And the concept in this problem is that we have a three-dimensional situation. Notice the tension we got in each of these ropes for an answer is the same. We got 23.6 newtons for both of those guys, and that comes from the symmetry of the problem because they're both the same length, they're just spread, and one's pointing behind the plane and one's pointing in front of the plane. But we have this guy, we draw a free body diagram, we need to find vectors for everything. So we go and we find vector AB by its magnitude times a unit vector in that direction. Here's the vector FAB. Same thing for the other guy. Its magnitude times a unit vector in that direction, so we find that vector. The AD vector was very easy to find. The weight vector was very easy to find. Once we have everything in Cartesian form, we can just add them together. This enormous addition is just adding all the vectors together. The secret is when you add vectors together, the only way you can add them is to add them component by component. We've been doing that all the time. When you add vectors together, you add the x components together, and you add the y components together, and you add the z components together. So when you have a vector sum like this and you set it equal to 0, what you're saying is that the sum of the x components has to be 0, the sum of the y components has to be 0, and the sum of the z components has to be 0. And that's exactly what I was doing here, component by component. The I components sum together 0, j components sum together 0, k components sum together 0. Boom, there's your answer. And that brings me full circle back to where we started from. The condition of equilibrium can be written in many ways. You can write it compactly, just saying, hey, sum of the vectors is 0. You can break it out a little bit more and say, hey, I'm going to sum the x components, and that's going to form an I direction and a j direction for the y components and a k direction, and I'm requiring that all of these is 0. What it implies is that this has to be equal to 0, this has to be equal to 0, and this has to be equal to 0. When we write those down separately, we call it the scalar form. But really, it's the same condition. All you're saying is you add the vectors together, and that implies the components have to sum to 0 in order for this thing to not move, which means it's in equilibrium. So that's enough talking. I'm going to do a couple more problems to give you some practice with this, but we're just extending the techniques of two-dimensional analysis. It's a little more bookkeeping, so typically we use the vector formation a little bit more commonly in these problems because it's a little difficult to find the vector components. Notice we didn't give you angles here. We didn't do cosines and sines to find the x and y components. That's easy to do in the xy plane. It's harder to do in a three-dimensional problem. So typically in three-dimensional problem, you'll be finding the full-blown three-dimensional vector representation, then summing them together. Component by component is typically where you end up in the end game. And then you'll typically end up with a system of equations to solve algebraically to get your answers. So make sure you understand this, solve it yourself, and then follow me on to the next problem where we will continue getting practice. Learn anything at mathandscience.com.